Hello. In this video, we are going to look at Pople-style basis sets in more detail. In these sets, an orbital has the following form at some coefficient times a power of x times a power of y times a power of z times an exponential function, which is a negative exponent times r squared. In this case, x, y, and z are the x, y, and z axes. The values L, M, and N are non-negative integers. The exponent gives us some idea as to the extent of the orbital, and R is the distance of the orbital from the atomic center. Each of these expressions is commonly known as a Gaussian. An orbital can consist of just one Gaussian or a linear combination of Gaussians. Here is what we get in Gaussian if we use the GFInput keyword, giving us information. Here we've selected just the information for the element carbon within the 6-311G basis set. Here is the same information for the 6-311G basis set for the element carbon, but now with various values color-coded. The integer numbers that we see in light green, near the top we see a 6, and then we see a 3, and then we see the number 1 two different times, which are colored in green, tell us exactly how many Gaussian functions are combined linearly to make up one atomic orbital. The numbers that we see in red are the exponents for the Gaussian functions. The numbers in blue are coefficients. Notice that the numbers for the exponents and the coefficients are written in scientific notation. If one wants to use these numbers directly in Microsoft Excel, which is the same program that I've used to visualize the orbitals in this video, one has to make the minor change of changing the D's to a letter E. If you copy it directly as it is formatted on the screen, which is how it comes from the Gaussian suite of programs, the Microsoft Excel program interprets the values as text and not as numbers. So if you merely change the D's to E's, then Excel will recognize the number as a number in scientific notation. In the 6-311G basis set, the 6 at the beginning tells us that each of the core orbitals are going to be approximated by a linear combination of 6 Gaussian functions. For the element carbon, the core orbital is going to be the 1s orbital. So here we see in gray the information for the carbon 1s orbital. And we notice the number 6 in green, which tells us that this 1s orbital is going to be modeled by a linear combination of 6 Gaussian functions. The numbers in red, as we mentioned before, are the exponents of those Gaussian functions, and the values in blue are the coefficients for the linear combination to make the 1s orbital in carbon. Here in Table 1 is exactly the same information, but now in a table format, and with each of the Gaussians involved from 1 through 6 listed as a row in the table. Here we see the exact mathematical form of each Gaussian, listed as G1 through G6, with the coefficient omitted temporarily, showing how the exponent fits into the overall formula. And then we see that the 1s orbital is modeled as a linear combination of these Gaussians, and the coefficients of that linear combination are exactly the values in blue that we saw in the GFInput output and in the table 1. In this figure, we see plotted in Microsoft Excel the values of each of the Gaussian expressions, and then in the more solid dark blue line, their total linear combination. One thing to point out is how each of the Gaussians has the typical Gaussian bell curve type shape, but when we have their linear combination, we get a more pointed value that looks more like a Slater type orbital. And we recall that the solutions to the Schrodinger equation for the atomic orbitals have the form of Slater type orbitals rather than Gaussian type orbitals. We use Gaussian orbitals because it makes the mathematics easier, particularly when we have a large number of orbital functions. For carbon, once we get to the 2s and 2p orbitals, we are now in the valence shell. So in the 6-311G basis set, it tells us the information after the dash that each valence orbital is going to be modeled as three distinct functions. So essentially, the 2p x orbital, there's three different versions of them. The first is made up from a linear combination of three Gaussians. That's what the first three in 311 means. The second 2px orbital is a single Gaussian. That's why we have a number 1. And the third 2px orbital is again modeled as a single Gaussian, and that is where the last one in the 6-311 comes from. So here we see in the output from the GFInput keyword the information that the program uses to construct these orbitals. So we see not just S or P individually, but we see the combination SP. And this region is highlighted in gray. So this is just for the first S or P function, the one that is made up of a linear combination of three Gaussians. So a trick that is used for S and P orbitals in the second shell, the 2s and 2p, is very common in computational chemistry programs, is we notice that we have the exponents, which are shown in red. But then we see we have two columns of coefficients, which are shown in blue. The first to the left, and then the second to the right, which is also underlined. So a technique that is used is to make the S and P orbitals have exactly the same exponents. So that's why we don't have to reuse exponents, because we just have one column there. We use exactly the same whether we're talking about an s orbital or a p orbital. What is different is their linear combination, and we'll see there's also one other minor difference. And so the coefficients change. The first column to the left is the coefficients that we use for the 2s orbital, and then the column to the right, which is underlined, is the set of coefficients that we're going to use for the 2p orbitals, whether 2px, 2py, or 2pz. Here in tabular form is the information for just the 2s orbital, the one that's going to be modeled with three Gaussians, showing the exponents, the coefficient, and individually numbering the Gaussians. This is exactly the same information that was shown in the previous slide, but made into a table form to make certain things clear. Here we have written out explicitly the forms of the three Gaussians which are used for the first function to represent the carbon 2s orbital, showing the exponents clearly in red, and then that the 2s orbital is a linear combination of those Gaussians with the coefficients that were shown in the table and in the GFInput output. Here we see plotted in Microsoft Excel the Gaussian expressions, one of which is shown in green, is barely visible. But then we see in black their overall linear combination to form the first of the 2s orbital functions, the one that involves three Gaussians. Here in Table 3, we have the exponents for the 2p orbitals, the ones that are formed from a linear combination of three Gaussians, showing the exponents, which are exactly the same exponents as we used for the same function for 2s, but showing now the different coefficients that were optimized for the 2p orbital. Here we have the Gaussians involved in the 2px, for example, orbital that is formed by a linear combination of three Gaussians. And if you compare, you'll notice that these Gaussians have exactly the same form as the Gaussians that we used for the 2s orbital. But the linear combination that is listed under 2px with a 3 after it is different because not only does it have different coefficients, which are shown in blue, but to make it a p orbital and not an s orbital, it is also multiplied by x, by the x coordinate. So x times a Gaussian will give us a p-type orbital, specifically the px orbital. If we had y times the Gaussian, we'd have a py orbital, and so on. Whereas if we don't have an x, y, or z, and we just have the Gaussian and its coefficient, that is suitable for representing an s orbital. And that is how we get the different orbital nodes for s orbitals as opposed to p, and to get the right distribution. Here is a plot of the three Gaussians. Again, in green, we see one very, very small, which doesn't contribute a whole lot. It's hard to see on this particular figure, but we can see the individual Gaussians, and then in black, the linear combination, which represent the 2p orbitals for the element carbon. Notice how the function goes to 0 at 0, accounted for the fact that we have a node in the p orbital at the origin, whereas the s orbitals do not have a node at the origin. And in fact, s orbitals can actually have the possibility of an s orbital being in the nucleus, which is impossible for a p orbital because of the node. So here is a plot of the 1s, 2s, and 2p orbitals for carbon as modeled as a linear combination, 1s being a linear combination of 6 Gaussians, the 2s and 2p being modeled as a linear combination of 3 Gaussians. So we can see the slightly different shapes of the 1s and 2s, particularly how close the electron density is to the nucleus. And we see the vastly different shape of the 2p orbital, which has a node at the nucleus at r equals 0. Recall that we still have two more different 2p functions, which are each modeled as a single Gaussian. So this is just 3 of the 5 total functions, and these are the functions that involve a linear combination of more than one Gaussian to form the orbital. Recall that in the valence shell, each of the valence orbitals, whether 2s or 2p, are going to be modeled by three different functions. The first function consisting of a linear combination of three Gaussians. The second and third functions each being a single Gaussian. So on this slide, we actually show all the functions that are used to represent 2p orbitals. So we see, for example, the first function used for 2px, for example, consists of a linear combination of three Gaussians. We've already seen this one before, so it's put up on there for reference, so we see that we did not forget about this one. Then we have two more functions to represent the carbon 2px orbital, for example. And in parentheses after it, I have how many Gaussians. So we see a 3 in parentheses, a 1, or a 1. It tells us exactly how many Gaussians are involved. So in the second function for 2px, consists of one Gaussian, and we show that it has a particular exponent of minus 4.8 times 10 to the minus 1. And then the third and final function used to represent the carbon 2px orbital is going to be this x times the exponent of minus 1.46 times r squared. So here are the three different functions that are used to model 2px. So when we say that we use three different functions, we mean three different functions for each of the 2p orbitals. So there's three functions for 2px, there's three functions for 2py, and there's three functions for 2pz. Now it may seem strange to do this, but it yields more accurate answers, which is exactly why it is done. Here we have the text of the GFInput keyword showing the information for the second 2p function, which is the exact same information for the second 2s function. We see that in green there's exactly just one Gaussian, and then we have an exponent shown in red. And you'll notice that the coefficients for both s and p, the leftmost in blue is for s, the rightmost in blue and underlined is for 2p, is the number 1. This makes sense because we're only taking a linear combination of one Gaussian, so its coefficient is simply going to be 1. This will always be true when we have so-called uncontracted functions. Uncontracted functions are ones that only consist of a single Gaussian. Here is the relevant information for the third and final 2s or 2p function. Again, we notice that it has a single Gaussian, so we see the 1 in green. We have an exponent, which is exactly the same whether we're talking about 2s or 2p. And then we notice that the coefficients in blue, though they're written in scientific notation, are simply the number 1. This will always be true when we have so-called uncontracted functions, functions that consist of only a single Gaussian. Here are displayed in Microsoft Excel the three different carbon 2p functions. We notice the one in black is the one that is a linear combination of three Gaussians. The other two functions, shown in red and blue, are the functions that consist of only a single Gaussian. And we notice that the relative extent, how close to the nucleus each of these is very slightly different. It turns out that representing a valence orbital by three different functions, we say it is triple zeta quality because there's three functions, gives better agreement with experiments than does double zeta, where we would model the 2p orbital with just two functions, or having only a single carbon 2p function. So though it may seem very unnatural to a chemist to think about there being three different 2px orbitals on just one atom, it turns out that this is absolutely necessary to get good agreement between computations and experiment. I thank you very much for your attention. I hope everyone stays safe, stays healthy, and as always, have a good one.